Hello, you're welcome to the chemistry class for today, and we'll be talking about isotopes. Yes, so what are isotopes? Now, isotopes are atoms of the same elements which have the same atomic numbers but different mass numbers. I'll take it again. Isotopes are atoms of the same elements which have the same atomic numbers but different mass numbers. Now, before we move on to explain these things, let's give a concise definition of what we call atomic numbers and mass numbers. Now, let's start. In an atom, it is composed mainly of three fundamental parts, which involves the proton, which involves the electron, and which involves the neutron. Now, the proton is said to be the positive part of an atom, the electron is said to be the negative part of an atom, and the neutron is said to be neutral. Now, the number of protons that we actually have in an element is what we call or what we refer to as atomic numbers. Now, how do we represent atomic numbers? Atomic numbers, in case an element is written as a subscript. Now, what do we call a subscript? Like, the subscript is that number we write towards the end here, the small number here. So if you see a number and it is written as 15, and it is an element, you are told that it's an element and it is represented as 15. If you see this number here, please bear in mind that it is indirectly telling you that this element A has an atomic number of 15. That means it has 15 protons present in it. But now let's get to the term mass number. Now, what is mass number? Mass number is simply talking about the number of protons and neutrons that is being present in an atom. I repeat, it is the number of protons and neutrons present in an atom. And how is it indicated? It is represented as a superscript. I repeat, it is represented as a superscript. And what do I mean by the superscript? The superscript is the number that is written as the top. So you can see a number written as maybe 20. What this is telling you is that this 20 is an indication of the sum total of the proton number and the neutron number present in an atom. So by reason of this, it is not, you can't indicate the number of electrons that is present but with these numbers. Please, it is strictly talking about the proton and the neutron number. And that is for the number at the top, which is the mass number. And this one is the atomic number, which talks about the number of protons. Now, let's talk about some, little calculations as regards this. So by reason of this, if you have a mass number given and you have an atomic number given, you can use it to identify the number of neutrons. Yes, because when you have your mass number subtracted or subtracting your atomic number, what you actually have is your neutron number. So in this case, if I ask you what is the number of neutrons present in this particular element, you would say that the neutron number is equals to this figure you're getting here, which is 20, minus this figure here, which is 15. Hence, we will say that our number of neutrons here is 5. So this is a brief introduction of what mass number and atomic number means. Now let's get to what we call isotopes. As I earlier said that isotopes are atoms of the same element that has the same number of protons but different number of mass numbers. That they have the same atomic numbers but different mass numbers. In this case, we would have something like this. If I to represent an atomic isotopes, this is how it should be. You have something like, let's still work with the A we are representing the element as. So you can have something like 15, and you can have something like 20, and you still have something like A21, 15, A22, 15. Now, if you look at this, we can refer to these things as isotopes of A as an element. Isotopes of A. Now, what's the difference? The difference between isotopes is their neutron number, because you can see that the atomic number are all the same, but the neutron numbers will differ because of the difference in their mass numbers. Because when you subtract this from this, you'll be having 5 neutrons. When you subtract 21 from 15, 21 minus 15, when you carry out this calculation, you'll be having 6 neutrons, and 22 minus 15, you'll be having 7 neutrons. So you can see that they differ by the number of neutrons that they each possess. Now, in nature, do we actually have elements that have isotopes? Definitely we do. Now, when you go in nature, the first element we all know of, which is hydrogen. Hydrogen do have isotopes like this. This is the first one. This is the second one, and this is the third one. Now, this is the first one. This is the first isotope of hydrogen, which is regarded as protium. This is the second one, regarded as deuterium. And this is the third isotope of hydrogen, which is regarded as tritium. Now, this particular one is said to occur more in nature, but these two are said to be radioactive. Deuterium and tritium are said to be radioactive. Now, if I should ask you what is the number of neutrons present in protium, what's going to be the answer? You can do the quick math. As I said, the number of neutrons is always going to be gotten by what? By carrying out subtraction here. So it is going to be your mass number minus your atomic number, which is 0. So protium actually has 0 neutrons. It has 0 neutrons. But what about deuterium? Deuterium, you're having 2 minus 1. Deuterium actually has 1 neutron. And what about tritium? 3 minus 1. It has 2 neutrons. So this is one thing about isotopes. They differ by the number of neutrons. Now we have established this. Now we can use isotopes to actually carry out calculations on what we call relative atomic mass. Relative atomic mass. Now, if you actually study your periodic table and you look at the different elements of the 118 elements that we do have, you would actually realize that even when elements are represented on the periodic table, even when they are represented on the periodic table, there are still some figures you will see by the side or even on top that it has like decimals. For example, you would see hydrogen represented as like this, but you will still see another figure again by the side that is written as 1.008. Now, this figure you're seeing here is what we call the relative atomic mass. Now, what does the term relative atomic mass mean? Now, relative atomic mass simply talks about the mass of an element as compared to 1/12 the mass of carbon 12. Now, need I tell you that hydrogen is not the only element that has several isotopes? Yes, we have other elements. Let me give you examples. For example, carbon, as I said. Now, this is carbon. There are several isotopes of carbon. We have carbon represented as this. We have carbon represented as this. We have another isotope of carbon represented like this. Same thing applies for chlorine. You have chlorine represented as this. You also have chlorine represented as this. So all these things are isotopes of chlorine, and these are isotopes of carbon. So it is applicable to so many elements. So the thing is, when you see the relative atomic mass of an element represented as decimals, when you see the relative atomic mass of an element represented as decimals, for example, as I said, you see that of hydrogen like this. Chlorine is mostly represented as 35.5. Some actually presented as 35.45. And there are so many. Copper represented as 63.5. Now, there are so many. So when you see relative atomic masses of elements having decimals, what does that imply? That means that that element is isotopic in nature. What do I mean? It means that that element has several atoms of different elements that have different mass numbers. Now, as I said, can the relative atomic mass of elements be calculated? Yes, it can. And with isotopes, you can actually calculate it. Now, how do we calculate it? You can calculate it using two methods actually. The first method is by the percentage occurrence in nature, and the second one is by the ratio, the degree of ratio that they occur in nature. Now, we are going to carry out calculations using two methods, and by the end of this class, hopefully, you will understand better how to calculate relative atomic mass. Okay, now let's start with our first example. Let's start with chlorine. Now, for chlorine, let's say we have chlorine represented as this and this and this and this. Now, these are the two different isotopes of chlorine, but their occurrence in nature. This particular form of isotope is occurring at 75%. This is the abundance you have in nature. This is the abundance of chlorine isotope with mass number 35 that occurs in nature, and this actually has 25%. Now, with this, how do you carry out the calculation? The calculation is actually carried out by multiplying the mass number, and the percentage occurrence, and you add both of them, and the net mass is actually what gives you the relative atomic mass of any element. Now let's carry out the calculation for better understanding. Now let's try. With this, you will have this one here, which is having the mass number of 35. You carry it out as 35 times the percentage in nature, which is 75. You divide it by 100. It is in percentage, 100. Then you add it to this particular one here, which is 37 times 25 over 100. Now, if you carry out your calculation properly, this would actually give you 2,625. Okay, for better clarity, let me solve it here. If you carry out this calculation properly, this is actually going to give you 2,625 divided by 100 plus this particular one here would give you 925 divided by 100. And if you carry out this division, it will give you 26.25, and this will give you 9.25. And the net, the sum of everything would actually give you 35.5. Now, this is the relative atomic mass. So this is the relative atomic mass of chlorine, the chlorine atom, 35.5. 35.5. That's how to carry out the calculation based on percentage. Yes, based on percentage. Now we can actually go further to carry out more calculations. This time around, we can carry it based on ratios. Based on ratios. We've done the one of percentage. Now let's carry out based on ratios. All right. Now let's say we actually have something like this. Now these are
The same.
different elements having different mass numbers, and let's say they are occurring in ratios of 1 to 3. Now, with this, how do we carry out our calculations? It is going to be carried out by multiplying the mass number times the ratio at which it occurs divided by the total here, the total of the ratios at which they occur. Now, this is what I mean: 14 times 1 over 1 plus 2, 3 plus 2, 3 plus 3, sorry, 6. So you have 14 over 6, and this particular one here will be 15 times 2 over 6. And this particular one here will be 16 times 3 over 6. Now, if you carry out this calculation, you'll be having 14 divided by 6 plus 30 divided by 6 plus, and you have here 48 divided by 6. Now, when you carry out your division here, you'll be having 2.3, and this will give you 5, and this will give you 8. And in total, what will be the answer you get? The answer you'll be getting here will be 15.3. 15.3. Now, need I say this? The number you're always going to get as your relative atomic mass must always fall within the range of the numbers that they occur. That means your number must not fall outside the highest number of the mass number or the least number. So you are never going to get something anything like 16 point anything, or you're not going to get anything like 13.99 anything. It has to fall within the range of the numbers you're getting as the mass numbers of the occurring isotopes. So literally, this is how to carry out calculations on isotopes. This is how to carry out calculation on isotopes. You can carry it out based on the percentage occurrence. You can carry it out based on the on the ratio occurrence. So to finalize this, I can go on to give you one more example for better clarity. So imagine you have an element represented as A, or maybe you've been using a lot of A. Let's work with B. Imagine we have an element represented as B, or whatever B, and it is represented as 10, and this one is represented as 11. I mean their mass numbers now. And when you have something like this, now imagine that we said that the occurrence of this thing in nature. Now we're working with percentage now. If the occurrence of isotope B, this here, let's give their symbols to their atomic numbers to be 2. Now imagine they have something like this, and you are told to carry out a calculation on their relative atomic mass. And the percentage occurrence of this particular one here is 20%, and the percentage occurrence here is 80%. So how do we carry out our calculation? Our calculation will be carried out by multiplying 10 times 20 over 100 plus this particular one here will be 11 times 80 over 100. So you know what to do next. This will be 200 divided by 100 plus this particular one here will be 880 divided by 100, and in total you'll be having 2 plus 8.8. And what's that going to be? That's going to give you 10.8. So literally, this is how to carry out calculations on isotopes in relation to relative atomic mass. Now, how do I finalize this statement? Now, I would to the viewers watching, I would like you to carry out some calculations on your own and give me your answers on the comments. Let's really understand if we let's really know if we properly understand the topic. So I will give you some questions to solve. Yes, I'll give you some questions to solve, and when you give me your answers, I will verify if you're correct or not. So these are the questions you should work on. Now imagine you have an element represented as X, and it has 3 different isotopes, and these ones, let's say the mass numbers are represented as 40, 41, and 42, and their percentage occurrence respectively happens to be 30%, 30%, and 40%. This is going to be your number one, and let's work with our number two. Our number two question, let's work with it in terms of ratios. Now, let's say our element is represented as W, and this other one too is W. And in terms of their mass numbers, let's give it a figure of 50, and this one has 51. Now, bear in mind that W is actually tungsten. It's actually the element's tungsten, but we are working with it imaginary. So it's not like this is tungsten. This is not the mass number of tungsten for clarification purpose. Yes, but This is represented like this, and we all know that the mass numbers, the atomic numbers are going to be the same. That's why I'm not actually representing anything down here since we are not even working with it. So now let's say we have something like this, and their ratio happens to be 3 ratio 3, 3 ratio 1 actually. So please, I'll need you to find the answers to this and give me the feedback on the comment section. Thank you very much. So I know one way or the other you have been educated from the video you just watched. So I am appealing that to get more educative content like this, please do like, subscribe, and it promises to be more educative as it goes on from now. Thank you very much and see you in the next video. Thank you.